So in this video, I'm going to solve some question for your final exam. These are like the review question for chapter 8. So, but before I'm starting the first question, I just wanted to make sure this question, I think I forgot to talk about it. So I just wanted to make sure that you guys consider that. So we have the loss coefficient in this question for inlet and exit, which are each 0.5. So we have KL here and a KL at exit. So when we want to calculate the sigma KL, we have 7 times 1.5, which are because of this threaded 180 return band, and we have 2 times 0.5, which is for the exit and inlet of the pipe. So now let's go to the question that I want to solve. So this question. So we have a large tank that is open to the atmosphere, and the fluid in this question is water, which is at 5 degrees Celsius. So then we have a pump that pump the water out of the system through the system, and then these are some information about the pipe. Like, okay, let me just highlight it for you. So these are the information that we have: the diameter. Also, we have the volumetric flow rate of the pipe, and then here is also P atmosphere. Here is P atmosphere, and then what else we have? And yes, that is what we have. Now the question asks us to find the power. So for finding the power, we know that the formula for power is if we have W dot of shaft, right, over M dot G, this is going to be our HS, right? So we can solve it for W dot, or also we can have W dot of shaft over gamma Q. So we have W dot of shaft. If I solve it for that, gamma Q times HS. So here we need to know what is HS, right? Now let's write down the energy balance for, if we consider this one, which is free atmosphere, as 1, and then here after the pump at 3 and before the pump at 2, right? So from here, if I write down the equation, so P3 over omega plus V3 squared 2G plus the height, and then P1 gamma V1 squared 2G C1 HS minus HL, right? So if I consider this location as my datum, right, so it means that then my Z is 0, my Z1 is 0, right? And then, oh, not Z1, sorry. So let's just consider this this location at datum, right? So then we have Z1 here and we have Z3 here. So also what else we have? So P3 and P1, these are both P atmospheres, so these are going to be 0. And V1, if we say that this is a large tank and this is a small pipe, right? So if we consider the conservation of mass, right, V3A3. If we consider the conservation of mass, we can say that V1 is really smaller than V3 because of the area, because A1 is really bigger than A3, right? So we can also ignore that one. Oops. So we can say that the V1 squared compared to V3 squared is 0. Now we need to know, so HS, we need to know HS, we need to know HL, and we need to know V3. So let's start for V3. So we know that Q is V3A3, right? So then it means that if we solve it for V3, we have Q by A3. And we know A, we know Q, so we can solve it for V, which is going to be equal to 8.49 meter per second. And then now we know V3, right? We know Z3, we know Z1, and now let's solve this for HL. So for solving for HL, we need to know that if we have turbulent flow or fluid envelope flow. So for knowing that, we need to use the Reynolds number. If I use the Reynolds number, I'm going to get 1.68 times 10 to the 6th, which is bigger than the critical Reynolds number. So then it means that we have a turbulent flow, right? And then from here, we can also see if it's fully developed or not. So the formula that we have is SLE 4.4 times Reynolds number times Reynolds number, right? So the diameter that we are going to get from here is 14.4 meter, which is less than the 30 meter, which is the diameter of the free jet. And so now, so not the diameter of, oh, not the diameter, it's the length right here, right? You can see the length on the picture. Okay, now let's go to the values we have. Now we need, okay, we were talking about HL. So when we said that 14.4 is less than 30 meters, so it means that we have fully developed flow, right? So fully developed flow. So now we have fully developed here, and from here we can find the HL, and we know that the formula for HL. So let me just write down the last formula we're gonna get out of this one. So the epsilon, if we are using the Moody chart, at the end we're gonna find F, right? So this is the epsilon that we have, and then the epsilon over D is this, and now because we have the relative roughness and we have the Reynolds number, we can easily find F with the Moody chart. So this is the value that we are going to get for it. And then now if we go back to the energy equation that we have, now we find HL. So let's solve it for HS. if we solve it for HS, this is the value that we're gonna get, and then we need to put that HS here, right, in this equation. Let me just highlight it here. If we put HS here, we know Q and gamma. So this is the final answer for the power, which is W dot is equal to 184 kilowatt. So this is what we have for this question.